Hi guys, this is Venu from NRI Institute of Technology. In this session, we are going to discuss about the topic duality principle in machine learning. As let us initially know what is a duality principle. For every problem, there is two type of problems. That first one is primal problem and the second one is duality. Here, every LPP is associated with another problem that is called a dual, and the original problem is referred as primal problem. For converting the original problem into duality problem, there are several steps to be followed. Let us discuss the steps. First, initially we have to convert the given primal problem into canonical form. That is, for maximization, the constraints should be less than or equal to its solution. For example, if the constraints are in x1 and x2, then the equation is ax1 plus or minus bx2 less than or equal to c. Here the constraints x1 and x2 and the equation is ax1 plus or minus bx2 less than or equal to c. Here the symbol less than or equal to represent the canonical form. That is, for maximization we took less than or equal to symbol. Same as for minimization problem, the constraints, that is x1 and x2 equation, we should take greater than or equal to. That means ax1 plus or minus bx2 should always greater than or equal to c. These are the canonical form conditions. And the second step is convert the canonical form into dual form by using the following steps. That is, for transferring the canonical form into dual form, first you have to transport the coefficients of objective function with constraint solutions and transport the columns of constraints into rows of constraints in dual problem. While we explain the example, you can understand these 2 points. And the third step is, if the constraint consists of less than or equal to in canonical form, then change it to greater than or equal to in dual form. And the same as, if the constraint consists of greater than or equal to in canonical form, change it to less than or equal to in dual form. These 4 steps you can understand while we are going to explain the example. First, the example is, write a dual form for the following problem. Here, let us consider an example. For maximize, the objective function given is z is equals to 50x1 plus 60x2, and the subjective to the constraints x1 and x2 is 2x1 plus x2 less than or equal to 300, 3x1 plus 4x2 less than or equal to 509, 4x1 plus 7x2 less than or equal to 812, and here x1 x2 are greater than or equal to 0 as they are non-negative constraints. First, you have to write the given data, that means the objective function and the maximization subjective. Here the subjective to the object is in canonical form. That is, for maximization, the condition is less than or equal to. In the problem, they are already given. For maximization, the constraint should be less than or equal to. They are already given less than or equal to condition. For example, if there any greater than or equal to, here you can see 2x1 plus x2 greater than or equal to 300. If the equation is in the form of greater than or equal to constraint, then convert it into less than or equal to by simply multiplying with minus, as minus 2x1 minus x2 less than or equal to minus 300. That's it. It's very simple. And now here they are already in the canonical form only. And here you can observe that clearly we can form a matrix with the coefficients of the constraints of these equations. That is, we got the matrix as like this 2 1 3 4 and 4 7. And to convert the LPP into dual form, first we have to assume that new variables, that is w1 w2 w3 are variables representing the constraints. That means in the places of x1 and x2 as the old constraints, we are assuming that new constraints W1, W2, W3 with respect to the equations. So from all above information, now we have to write the new objective function. The new objective function that we get is b is equals to 300 W1 plus 509 W2 plus 812 W3. That is, we make this for maximization, and here um, we get the objective function as this. From the subjective, the right hand side of the less than or equal to condition, that is 300, 509, 812. These values are combined with the new constraints, that is W1, W2, W3, and form the new objective function like this. B is equals to 300 W1 plus 509 W2 plus 812 W3, and the new subjective to the new constraints is the transpose of the matrix, that is the new subjective for the new constraints, that is W1, W2, W3 is taken from the transpose of the matrix as here 2W1 plus 3W2 plus 4W3. Here 2, 3, 4 is the transpose of this matrix 2, 3, 4, and the next one is W1 plus 4W2 plus 7W3 as this, and where W1, W2, W3 are greater than or equal to 0 as they are also non-negative constants. Now let us discuss the second example for duality principle. In the previous example, we discussed initially they given the condition that is in canonical form, but here you can observe clearly this is the objective function z equal to 4x1 plus 3x2, and the subjective to the constraint is 3x1 plus x2 equal to 3, 3x1 plus 4x2 greater than or equal to 6, x1 plus x2 is less than or equal to 4. This is the minimization form, and where x1 comma x2 are greater than or equal to 0 as they are non-negative constants. Here in this problem they given equal to, that means both less than or equal to and greater than or equal to are combined in equal form. So we can split equal to into less than or equal to and greater than or equal to. Then the data becomes like this. Z is equals to 4x1 plus 3x2, and this equal to equation can be written in two equation forms, that are 3x1 plus x2 greater than or equal to 3, and the next one is 3x1 plus x2 less than or equal to 3. Here for minimization problem the constraint should be greater than or equal to. So to form this less than or equal to into greater than or equal to, multiply with minus on both sides, we get minus 3x1 minus x2 greater than or equal to 3, and the third equation is 3x1 plus 4x2 greater than or equal to 4, and the fourth equation is in less than constraint, so we have to modify it into greater than. For that we multiply with minus on both sides, then we get minus x1 minus x2 greater than or equal to minus 4, and the next second step is we have to assume the new constraints, that is new variables w1 dash, w1 double dash, w2 and w3. Here we take w1 dash and w1 double dash instead of w1, as because both less than and greater than are derived from the same equation, that is equal to. For that we have taken like this, and the new objective function is b is equals to 3w1 dash minus 3w1 double dash plus 6w2 minus 4w3. Here it come from, as you can see that here the right hand side variable values are 3, 3 into w1 dash, and minus 3 into w1 double dash, and 6 into w2, and minus 4 into w3. From this we get the new objective function, that is for maximization, and the new subjective for the new constraints is the transpose of the coefficients of the old equation. Here the matrix form, that is 3 1 minus 3 minus 1 3 4 minus 1 and minus 1. With this matrix equation transform, we get the new subjective, that is 3w1 dash minus 3w1 double dash plus 3w2 minus w3, and the second subjective function is w1 dash minus 1 w1 double dash plus 4w2 and minus w3 is less than or equal to 3. That's it. And for that, here w1 dash and w1 double dash are derived from the w1, so we can combine both of them, that is make a common 3, then it becomes 3 into w1 dash minus w1 double dash. Instead of this, we can directly write w1. So the modified objective function is p is equals to 3w1 plus 6w2 minus 4w3, and the subjective to the objective is 3w1 plus 3w2 minus w3 less than or equal to 4, and w1 plus 4w2 minus w3 is less than or equal to 3, where w2 w3 are greater than or equal to 0 as they are non-negative constraints, but here w1 is equal to, so there is unrestricted, w1 is unrestricted, that means we cannot say that it is a non-negative or it is a positive. Okay, thank you.